Notes for section 10.6 and 10.7 are combined in one for today. So we're going to define a few terms and then we're going to talk about a few theorems. The definition of inscribed is a polygon is inscribed in a circle if all of its vertices lie on the circle. So let's draw a triangle with the vertices lying on the circle. So if I have all of that, there you go. Now, for the next term, we have circumscribed. A polygon is circumscribed about a circle if each of its sides is tangent to the circle. So tangent lines means they're only going to touch the circle once. So we'll try to do a quadrilateral. All right, close enough. And that'll be the center, and we can put the center like right there. Okay, so I would like to put some labels. Let's do A, B, C, D, and we'll put center E there. And we'll get back to that in a second. For circumcenter, the center of the circle circumscribed about a polygon is the circumcenter of the polygon. So we have circumscribed. So for these vocab terms that we're talking about, understand that polygon, or rather quadrilateral, A, B, C, D, is circumscribed about circle E. Or we could say circle E is inscribed in quadrilateral A, B, C, D. So they can go vice versa. All right. The incenter. The center of the circle that's inscribed in a polygon is the incenter of the polygon. Okay, let's talk about our theorems. Theorem 89 states that if two inscribed or tangent chord angles intercept the same arc, so intercept the same arc, then they are congruent. So let's draw two inscribed angles. So here's one inscribed angle, and another one could be like that. Because the arc for the blue angle is right here, and that is the same intercepting arc for the red angle, it means that these two angles are congruent. All right, you can also, if we had a tangent chord, that's not very circular. Okay, so if we did a tangent chord, so we'll make a tangent here and a chord, we'd have to use the same arcs. So I'm not super great at drawing these, but if we had a tangent here with the same chord, it's stating that this angle would be congruent to this angle because they intercept the same arcs. Okay. Theorem 90 states that if two inscribed or tangent chord angles intercept congruent arcs, then they are congruent. If we have this inscribed angle and the intercepting arc is that, and then let's do a tangent. So we'll do a line outside, that's tangent, we'll do a chord. Try to get it to look like that. If this arc and that arc are congruent, what we can conclude is that this angle is congruent to this angle. All right. Theorem 91. An angle inscribed in a semicircle is a right angle. So let's chop this circle in half and make a semicircle, which will be the bottom half. And let's put an inscribed angle in there. So if I put an angle from there to there, this would be 90 degrees. And you could actually have come up with this conclusion on your own because an inscribed angle is half of the intercepted arc. Well, if it's a semicircle, that arc is going to be 180 degrees. Therefore, this angle would be 90. Okay. Theorem 92 states that the sum of the measures of a tangent angle and its minor arc is 180. So let's make a tangent angle. Let's do tangent. So if I'm going to make this P, let's try to make this a little bit straighter. Okay. And then we'll make this T, center will be O, and this is S. So what they're stating is that the measurement of angle P plus the measurement of arc TS would equal 180. And with the rules you already know, you can come up with this. Let's say that this arc TS is 130 degrees. You know that the measurement, if you're trying to find the measurement of angle P, it's equal to 1/2 the arc right here, which that arc we can figure out as 360 minus 130, which gives you 230 degrees. So 230 is right there. So it'd be 1/2 230 minus 130. Well, this would be 1/2 of 100, which gives you 50. So now this new theorem is stating that this angle and the minor arc are going to have a sum equal to 180, which they do. All right, 93. Theorem 93 goes into section 10.7, which deals with quadrilaterals and circles. Okay? Theorem 93 states that if a quadrilateral is inscribed in a circle, its opposite angles are supplementary. So if I had a circle and this, try to draw it out, and it was A, B, C, D. So angle A plus angle C is equal to 180, and angle B plus angle D is equal to 180. All right. 94. Before we get to 94, we're going to read this story. It says, the story of the plain old parallelogram. Once there was a plain old parallelogram named rectangle. Rex was always trying to fit into a circle, that is. One day when he awoke, he found that he had straightened out and was finally able to inscribe himself. What had the plain old parallelogram turned into? So here we have a parallelogram, and it doesn't fit into a circle. But a parallelogram can fit into a circle only if it becomes and rectangle turned out to be a rectangle. Get it? Rectangle. Okay. On to theorem 94. Theorem 94 states that if a parallelogram is inscribed in a circle, it must be a rectangle. All right. Let's do some examples. Example 1. In circle O, so we'll put an O here, BC is the diameter. So we have B to C. And the radius of the circle is 20.5 millimeters. So we'll put 20.5 millimeters right there. Chord AC, so from C we'll draw point A. It has a length of 40 millimeters. They would like us to find AB. Okay, well, since BC is the diameter, we have an angle inside of a semicircle, which makes this 90. So if I remove this 90-degree triangle, I have a side that's 40, and this is 20.5. The whole diameter, which is the hypotenuse, would be twice that, which would be 41. Therefore, we actually have one of the families. We have a 9, 40, 41. So AB is equal to 9 millimeters. For example 2, we have parallelogram ABCD inscribed in a circle. So let's draw a parallelogram. And if it's a parallelogram, well, if these two are parallel and it's inside, we know that we have a rectangle. So label with the letters A, B, C, D. It says that the diagonals intersect at point E. Then it tells us that AB is 5, BC is 6, and they want us to find AC. Well, we know information about AB, BC, and we can easily find the missing side because that actually is the hypotenuse of your right triangle. So we have 5, 6, and we can say 5 squared plus 6 squared is equal to AC squared. 25 plus 36 is equal to AC squared. When you add that, you get 51. So, nope, I lied. 61. And then when you solve this, you would just take the square root of 61 is equal to AC. Okay, the last example. Example 3 says circle P. Let's draw a circle and put a center P. Okay, it has a diameter BC. All right. And AC, so from C we have to draw to A. That is 12 millimeters. B to A is 16 millimeters. And they would like to find the radius. Okay, well, once again, we have a semicircle and an angle in a semicircle, so we have a right angle. I'm going to simplify 16 and 12 by dividing them both by 4. So I have 4, I have 3, and that means it's a 3, 4, 5. To get the length of this hypotenuse, we would multiply by 4 to get 20. So from here to here, it's 20 millimeters, which is the diameter. The radius would be half of that, which is 10 millimeters. For the rest of today, you have 6 problems to complete on section 10.6, and then tomorrow and Friday, you will work on questions from 10.7.